Welcome to part 1 of the Calc 1 Exam 3 review. Let's hop right in and start looking at question 1. So, we are asked originally to sort of just interpret this statement, this integral statement, right? So, in this situation is that we have f of t, which represents the rate at which the U.S. consumes oil. Okay, and t equals 0 will be 2004. That just means we're starting at 2004. T is in years. What's the meaning of the integral from 1 to 7 of f of t? Well, it should immediately trigger in your head, since f of t is a rate, the integral of a rate will be like total consumption, right? So when does that consumption begin? That'll be in the year t equals 1, that's 2005, and it ends in 2011. I just took 7 plus 2004 there. Okay. Yeah, so integrals are like an accumulation of stuff, and we're accumulating the rate that we're consuming the oil from the years 2005 to 2011, and that is exactly what B says. The amount of fuel consumed in the U.S. from January 1st, 2005 to January 1st, 2011. Moving on, let's look at part 2 of problem 1. Now, for part 2, we're looking at rewriting an integral statement, as a right-handed Riemann sum. So, what we do for this, we need to first look at what the interval that we're integrating over. So we're integrating over from 1 to 4. That means a equals 1 and b equals 4, right? So the width, I'm going to draw a picture of this. The width of each little rectangle, we're starting at 1, we're going to 4, and we're breaking this up into a whole bunch of little rectangles, right-handed rectangles, like so. The width of each one of these rectangles, I'm just going to call delta x, but what will delta x be? It's going to be 4 minus 1 divided by the number of rectangles I'm breaking it into, or 4 minus 1 over n equals 3 over n. Using my formula for a right-handed sum, which is where we take the sum of whatever my function is, in this case it's a thing cubed. The thing that I cube is actually going to be a plus delta x times my counter. My counter here is k. It's just my index. I go up to n and I multiply by 3 over n. Well, delta x is also 3 over n, so that turns into 3 over n k cubed times 3 over n. And our a is equal to 1. So we have the sum, that's k equals 1 to n. And look at there, it matches up perfectly with number C. I mean letter C. All right, let's move on to the second page of the review. So here we're looking at part 3 of question 1. Okay. We are asked to, we're told that this Riemann sum is an approximation of an integral, but what is the integral that we're approximating? Okay, so first things first, I want to look at what numbers won't be a part of the integral. And what I mean by that is this 10, oops, this 10, it shows up here and here again. That's just the number of rectangles that we're using in our Riemann sum, right? Say the graph looks something like this. The upper part of the counter is just the number of rectangles that we're using. And actually, looking at this, that means that this is probably our delta x over n, right? Our n is 10, and that means our delta x will be 2, right? We're multiplying by the width. And how else do I know? Our k, our counter, is multiplied by 2 over 10 as well. So that's probably delta x. So we can say that delta x is equal to 2. And that actually immediately lets me cross off a few of these different answers. Like, I know it can't be that one, I know it can't be that one, and I know it can't be that one. How come? Because all of these go from 1 to 10. But delta x is 2, and 10 minus 1 is 9. That means we've got to be going from like 5 to 7, okay? And actually, 5 to 7, that's what this number is. This is your A. Your base point for where the sum starts. Okay. Well, if I look then, sorry for that. I'm also going to say this 4, it's just out in front. And just like these, they have the 4 out in front of the integral. So we're not sure what it is between this and this, right? So I'm going to tell you that the answer is A, right? But what about that 5 plus? Well, it doesn't matter. This 5 plus here, it doesn't go into the integral. Where it goes, that's where you start your integration from 5 to 7. It does not go inside of the actual function itself, and we know that the function is cubed. That matches up. What the heck is up with that k minus 1? Well, I'm glad you asked. If this were a right-handed sum, we would use k, but this is actually a left-handed sum, so we use k minus 1. Not a big deal. They just threw that in to kind of trick you. Moving on to part 4. Go in here. We are told that some function, has a negative derivative over, well, for all x between 5 and 9. So I'm going to go ahead and sketch a graph of what the function might look like. It doesn't necessarily look like this, but from 5 to 9, we have a graph that's going down, and it's always decreasing. Cool. So what they ask is which of the following approximations is the largest, right? So the left-hand rule, you'll take each of your rectangles, all of these, the first 3, we'll look at the last one in a second. They break the interval into 10 rectangles. I don't even know if I drew 10 little lines there. So our rectangles are going up, The heights of each one of these rectangles is set according to the function, but where? It depends on whether we're using the left hand, right hand, or midpoint rule. Out of the 3 places where a rectangle could touch, if the slope is always going down, the highest place is going to be on the left, right? You agree that this point here is higher than this point, which is what the height would be if you're using a right-hand rule. It's also higher than that point. So out of A, B, and C, L10 is definitely the largest. But what about D? Also, that immediately cancels out E, like they can't all be equal. What about D? Well, what D does, right, is it actually finds the area underneath the thing, the entire area. Right? So that's just the area under this line. But what L does, oops, we changed to red, is it finds the area of each of these rectangles added up. And if you notice, my drawing is not perfect. Each of these rectangles, they kind of go over the thing. Right? That means that L10 is an over approximation of the actual integral. So L10 will be bigger than the limit is in approaches infinity of the left-hand rule. Okay, so we're going to move on to part 5, and I believe this finishes up question 1. Oh no, there's also a part 6. For this problem, we're looking at a tank of water. Oops. Tank of water. And water is coming out at a rate of e to the... No. Water's coming out at a rate of t squared over 10. That'll be like gallons per second, because it's rate. Water's coming in at a rate of e to the negative t. There are initially 10 gallons of water. I am asked to find an equation that I can solve for x, where x will be the time in which the tank is empty. Well, I know with my equation, if I'm dealing with rates, and probably because this exam is over integration, we're going to have an integral, but what goes into it? What I'm going to do, I'm integrating from 0 to x, because x is my time. And my rate in, that's the water coming in, if I integrate that from 0 to x, that's how much water the tank gained. And I subtract my rate out, which the rate out integrated will be how much water the tank lost. So if I do rate in minus rate out, that's the total amount of water coming in or out of the tank, depending on the time. And I start with 10 gallons, so I'm going to add 10, and I want to know when that's equal to 0. Or in essence, when this is equal to negative 10. That's whenever this whole tank is empty, right? When I've lost all 10 gallons. All right, so I'm looking, and actually part B immediately matches up with this little equation I've written, so that's cool. Now, take a moment for yourselves and see if any of these other equations are the same as part B. And while one of them looks close, like solving the integral, A looks close, but I don't think that A is it. So I'm going to say I don't think any of them are actually the right thing. So it looks like to me that B is the only equation that works. And this is kind of a weird idea, that our variable is actually the thing that's in the integrating bounds. But remember, variables can pretty much go anywhere in math. The idea behind this is that if you want to know how much water is in the tank after an amount of time, you take rate in minus rate out. Rate in minus rate out, and you integrate. Okay, that'll actually finish up part 1 of the review. Go ahead and hop on for part 2, and I'll see you guys there.